If you build a very large simulation, it's not going to fit on one computer. You're going to find that you need multiple computers to execute it. And as soon as you cut it into pieces and distribute it across multiple computers so that it can execute in parallel, you're going to have a problem of keeping all of those pieces synchronized. You're going to need some mechanism so that the events in this queue are being executed at roughly the same time as the events in this queue, and that events that get spit out from this piece of the model and arrive at the second piece of the model are executed in the right order. Well, the parallel discrete event simulation community has created two large categories for doing that. One way to do it is called conservative synchronization. And conservative synchronization essentially treats all of these processes like a bunch of people who link their arms together and try to march forward. Before any one of them is allowed to move forward, it checks with the others to find out what simulation time it's at. And they all march forward in unison. They all stay synchronized all of the time. Then there's the optimistic simulation synchronization, in which every simulation is allowed to execute its events whenever it feels like, with no regard for the other pieces that are running on the other processors or on the other computers. And so he gets an event and he executes as fast as he wants. However, when he receives an event from another simulation, he has to guarantee that he has executed that event in the right order. And to accomplish that, what they do is they execute forward, and when that event arrives in their past, they undo all of their operations, roll back in time like a movie on rewind, go back, insert that event, and then re-execute that same queue again. So they're doing a lot of rework. And there's a lot of work that goes into how much can you gain from this by running ahead if you're going to have to back up. Well, how far ahead should I run, et cetera, et cetera. Those are the contributions of the parallel discrete event simulation community. The HLA runtime infrastructure makes it possible for you to link together simulations that are managing their events in all different ways. Some simulations are time-stepped. Some are event-stepped. Some use optimistic time management. Some use conservative time management. Some are real-time and don't consult other people's time at all, or don't try to synchronize at all. It's possible, under ideal conditions, to link all of those together and have all of those executing at the same time in the same virtual world. The RTI allows you to do that. It doesn't guarantee that you're doing it right, but it will allow you to connect them together and find out for yourself whether you can do it right. I want to show you Pritzker's modeling principles. Alan Pritzker is kind of one of the fathers of discrete event simulation. He's been around forever. Some of the languages I showed you were his invention. And he summed up 30 years of experience in building simulations and running simulation projects into 7 principles. And the first principle is conceptualizing a model requires system knowledge, engineering judgment, and model building tools. Okay? You have to understand the system you're going to model. The second one was the secret to being a good modeler is the ability to remodel. Every model you build is wrong the first time, and it's less wrong the second time. You're going to be reconstructing, reordering, reprogramming that model several times before you get it right. So your ability to be a good modeler is dependent on your ability to do that remodeling process. His third principle is that the modeling process is evolutionary, because the act of modeling reveals important information piecemeal. You don't build a model and then run it and learn all your lessons. You learn lessons every day that you're building that model. And so this leads to the rework example. If you're going to be a good modeler, you're going to know something a week from now that you wish you had known when you started the project but didn't. The modeling process is a learning process. You don't build it and then learn when it's done. You learn the minute you start building the model. So you're going to have to remodel. Number 4. The problem or the problem statement is the primary controlling element in model-based problem solving. This may seem obvious, but it's amazing how many people will come to you and say, I want you to build a simulation. And you say, what problem are you trying to solve? I don't know. I want a model of my factory floor. And why do you want this model? Well, because I don't have one. Well, what problem are you trying to look at? None, just the factory floor. They can't state why they're trying to have this model built. They can't state what its objectives are. And it's very difficult for you to solve their problem if they can't tell you what their problem is. That happens a lot. His fourth principle is modeling. When you model combined systems, the continuous aspects of the problem should be considered first, those differential equations. The discrete aspects of the model should be developed second. Okay? From his experience, that's the way it works out. A model should be evaluated according to its usefulness. From an absolute perspective, a model is neither good nor bad, nor is it neutral. A model is good if it's useful. If it helps you to learn things, it's good. If it doesn't help you to learn things or understand things, it's not neutral. It might be bad. And finally, my favorite one, the purpose of simulation modeling is knowledge and understanding, not models. We build models so that we understand the world better, not so that we have a beautiful artistic creation in a computer. We don't build a model so that we can represent a factory simply because we don't have a model of the factory. We build a model of the factory because there's some useful reason for having it. There's something we're trying to accomplish. There's something about that factory we don't understand. And the model is going to help us understand that. If it doesn't help us, it's not a good model. Those are 7 lessons from a man who spent 30 years learning what those lessons were. This slide shows you simulation project management skills. Another person at Alan Pritzker's company put these together, and it's really more than I can go through in detail here. But here's a sample of how he describes modeling a simulation project. If you want more detail, you can look at the article in the Handbook of Simulation. Where's this going in the future? Discrete event simulation is primed to go into all kinds of applications. You could use one of these simulations to manage your household control. It could manage the power, the heat, the water. It could manage all of the energy consumption in your house, do it more efficiently than you're doing it now, but create an environment that's more comfortable for you than what you experience right now. It could go into the auto mapping computers that tell you how to get from point A to point B. It could be sampling real-time data sources that know where traffic jams are, that know where accidents have happened, that know where construction crews are working, and tell you how to get around it at any time. You could put these simulation programs into scheduling software so that when you open up your Palm Pilot and you try to make a schedule, an appointment for a specific time, it advises you that what you're about to do is not reachable, that you can't get from point A to point B in time to make those 2 appointments, or that you've scheduled 2 appointments that require you to leave one 10 minutes early. It's very easy to incorporate this into all kinds of different models of things that you do every day. Here's the best reference I have on this. The Handbook of Simulation. It came out last year. It's a compilation of all of the major topics in discrete event simulation. It's a little bit pricey. It's like $125. Really steep. But it's better than most of the simulation textbooks, which you'll find on the shelf next to it. You can use it like a reference. You can turn to any. You want to know about random numbers? It's in here. You want to know about statistical distributions? It's in here. Output analysis? It's in here. Pritzker's principles? It's in there. Oh, by the way, I don't get paid for saying that. It is just such an excellent book that I have no hesitation at giving it a great recommendation. But if you don't need that information, don't spend your $125. It's a lot of money. If you need that information, it's well worth it. Well, that was discrete event simulation. Conceptual frameworks, random numbers, random variates, simulation languages, software tools, parallel discrete event simulation, and modeling principles. And that's essentially what we covered. This is the time when you take a break, and we'll move on to the next subject after you've had time to absorb what we just told you. We're going to conclude the class with a lecture on the permeation of simulation ideas into the entertainment field. It used to be very rare that you found blatant simulation applications in things that you did for fun and games. There were a couple of places where it's always been there, but it didn't show up in most people's day-to-day lives. Now it's showing up so many places that you won't be able to look anywhere in the entertainment field without seeing something that's driven by simulations. If you look into simulation as a form of entertainment, you can go back to games of war as early as 3000 BC. Again, I'm jumping way back in history, and I'm going to pull you through 5,000 years of history in several discrete jumps. I'm a discrete event lecture here. The game of Weihai emerged in 3000 BC, which was roughly around the Bronze Age. And then games after that kept emerging and emerging, and now you see them in your electronics boutique and things in the mall. In 3000 BC, the Chinese created a game which was called Weihai. We know that the term Weihai means encirclement. We know that they played on some kind of abstract board, and we know that they placed colored stones on that board. That's it. No examples of Weihai survived. No pictures of it, no carvings, no nothing. We think that Weihai is the father of the Japanese game of Go. In Go, people sit down at a board and play a strategic game in which they place stones on the board and are specifically trying to control large areas of the board, not capture the opponent's stones. It's a very strategic thinking game. You try to think about where do you place your stone now, but you think forward about how are you setting up the next move and the move after that and the move after that. You have to think of the long-term implications of each turn you take right now. Also in Africa and the Caribbean, a game called Mancala emerged. There are several different versions of Mancala, but the accounting groups used to use it when they were trading goods on the market. And it became a game in which you place stones in each of these cups, and as you take turns placing the stones, there are rules that allow you to capture your opponent's stones and place them in your Mancala cup. If you have kids, you might see them play Mancala today. It's been popular in the last year in some of the elementary schools. Chaturanga emerged in 500 BC in India. The Indians created this game in which you moved your pieces around on the board. You could play the game with 2 or 4 players, and it obviously looks like chess. Initially, you had to make your play decisions based on a roll of the die. But the Indian government started cracking down on gambling, and any game that used die was considered gambling, so they eliminated the die and let the player choose which piece he was going to move. Of course, Chaturanga of 500 BC was the father of chess, which emerged in Western Europe in 500 AD. And we've always considered since that time that somebody who was good at playing chess, good at thinking strategically, good at moving a piece now, but that's part of a larger puzzle that's unfolding several moves from now, that person would be good at controlling assets on the battlefield. And so there's always been this mystique that commanders who can play chess can manage assets on the battlefield. Board war games emerged in 1958, as I described earlier. Charles Roberts was really looking for a way to teach himself to conduct war, to command assets on the battlefield. And he ended up creating a hobby. And that hobby went on to be a very large piece of the entertainment industry. Those games that you play, the board war games, are rather complex. They're large rule books, there's lots of pieces. Playing out a complete scenario may take days and even weeks.